chapter 7. We looked at the solution lifting idea for generating solutions of polynomial congruences modulo prime, power of prime. And today we're going to start this topic of quadratic residues, and it's very much connected to what we've just been doing with polynomial congruences. But it focuses on quadratic polynomials and explores the idea of, is there something like a square root in modular arithmetic? And if so, how does it behave? What properties does it have? And it turns out to be quite an important topic, and you get some very powerful results out of it. So the result at the end of the chapter, which we build to, is called the quadratic reciprocity law, and that describes strong links between the system of multiplication modulo 1 prime and the system of multiplication modulo another one, and it connects what's going on with square roots in those two systems. But anyway, to get us started with this topic, I want to return to more familiar ground. So I return to some basic ideas. So everybody recognizes this kind of thing, this kind of question. Find the solutions of a quadratic equation. Okay? And everybody knows there's a nice formula for the solutions of this, which is minus b plus or minus square root b squared minus 4ac divided by 2a. Okay? It's the kind of standard formula. Probably learned it as part of your GCSEs, I guess. And it's something everybody knows off by heart. Okay, but let's just before we go on to the more abstract, perhaps, ideas of quadratic residues, let's just derive the well-known formula for its solutions. Now, we're thinking about solutions to this. It makes the algebra a little bit easier if, before we start going, we multiply both sides by 4 times a. Okay, we multiply both sides by 4 times a. Multiply the right by 4 times a, and still 0. And this is a logical equivalence. This equation will be true if and only if this one is true. I guess there's a slight proviso there, is that the a should be non-zero. If a is non-zero, the reason this is a logical equivalence is because this step that I've done, multiplying both sides by 4a, that's invertible. I can divide both sides by 4a, and I get right back to the equation I started with. Okay? So we're doing an invertible operation, so this is a logical equivalence. Both equations have exactly the same solutions. And the benefit of multiplying both sides by 4a is it makes it easier to kind of decompose the quadratic there through this process of completing the square. So if you then consider the square of 2ax plus b, square of 2ax plus b, well, this will give you certainly the 4a squared x squared bit. And it gives you 2 times this, so that gives you the 4abx. It doesn't give you the 4ac, and it also gives you a b squared that you don't want. So you have to subtract the b squared. This is where the minus b squared comes from. And we have to add on the plus 4ac. 0. So you continue the manipulation. So this is good now because we've reduced the x squared and the x down to just a single x. So you can continue to work on this. So you've got 2ax plus b whole squared. This will be equal to b squared minus 4ac. And you see the appearance of the well-known discriminant of the quadratic equation. And then you say this is equivalent to 2ax plus b equals the square root of this, b squared minus 4ac. And then finally, you make x the subject, so you have to have a minus b over here, plus the square root of b squared minus 4ac, and you divide by 2a. And there you finally got the solution. So hopefully that rings some bells for you, that kind of derivation. Now, there's a few little minor details that I've been a bit careless about there, and things I've skipped over. And it's to do with the existence of this square root. Can you take the square root of this thing? And is there just one thing that is the square root of that thing? Or are there multiple things? And part of this partly depends on what x is supposed to be in the very beginning. Are we only considering real numbers x, or are we going to broaden our scope and allow in complex numbers x? Or is this a mean, or maybe this is a means through which we can discover the existence of complex numbers, and forcing ourselves to believe that this square root will exist for every possibility. But we iron out some of those details I've skipped. First of all, if we insist that we're only considering real numbers x, then that forces you to be very careful about what you're doing here, okay? Because you can't always take the square root of a real number in order to get another real number. So what's the extra condition that goes along with here, or what's the kind of small print that goes along with here? I can only take the square root if this b squared minus 4ac is positive, okay? Provided b squared minus 4ac is non-negative, okay? Provided it's greater than or equal to 0, then this is a legitimate step. There will be another real number, which is the square root of this. But then we have to be a little bit more careful and precise. Actually, there's two possible real, well, in the case where it's 0, the square root is 0. But in all other cases where the square root exists, there'll be two square roots. There'll be a positive one and a negative. So that's why you have the plus and minus. So this is really plus and minus, okay? So these are logical equivalences fine, provided that this discriminant is non-negative, and if b squared minus 4ac is less than 0, then no real solutions. No real solutions exist, and that's clear because if this b squared minus 4ac is a negative number, what we're saying is that the original equation is logically equivalent to this one, and this one says the square of this real number is equal to a negative number, and that's just nonsense. Okay, the square of a real number cannot be equal to a negative number because the square of a real number is always non-negative, greater than or equal to 0. Okay. Any questions or queries? So that's a reminder to you about how we mathematically deal with finding real solutions of a quadratic equation. Of course, the description is slightly different if you're allowing x to be a complex number, and of course these square roots always exist. It's still only going to be 2 of them. Okay, so what we'd like to do now is attempt to do the same thing with modular arithmetic. So let's attempt to make the same argument, or a similar argument, for this problem, which is solve ax squared plus bx plus c congruent to 0 modulo p, modulo prime. Well, I'll just try and perform exactly the same steps that I performed before. So the first step was to multiply both sides by 4a. Okay, I can still do that. I can multiply both sides by 4a. I'll have 4a squared x squared plus 4abx plus 4ac congruent to 0 modulo p. Be a little bit careful about what I'm doing here. If I want this to be a logical equivalence, you need that step to be invertible. So I need to be able to say this equation implies this one, which it would. That's true simply by multiplying both sides by 4a. But to get the reverse implication that the second equation implies the first, you have to be able to divide both sides by 4a. Now, what we mean when we say divide both sides by 4a, what we really mean is multiply both sides by the inverse of 4a. So the inverse of 4a has to exist, because sometimes it won't, because we're dealing with multiplication modulo something, so not everything has an inverse. So we can ensure that there will be an inverse of 4a if the prime number p is co-prime to 4a. And how could we arrange that? Well, there's the factors of 4a are 2 and whatever the factors of a are. So if we ask that 2, that we're not talking about the prime number 2, so if we insist that we're talking about an odd prime, so we'll disregard the prime 2, and furthermore that a is co-prime to p. Okay. So this will be a logical equivalence provided p is strictly greater than 2 and that p does not divide a. I mean, if p divided a, it wouldn't really be a genuine quadratic congruence we're looking at, because that would be 0 in effect if p divided a, because the a would be congruent to 0. So it wouldn't really be a quadratic. So provided we're not talking about, I mean, the prime 2 isn't that interesting. There's not that much that can happen with 0 and 1, arithmetic involving them with regard to quadratic equations. So provided p is greater than 2 and a is co-prime to p, or in other words, p does not divide a, so p is a prime number, so that's the equation that condition is equivalent to. That is so we have this logical equivalence here, and then you can play this game of completing the square, no bother. Plus minus b squared plus 4ac, that still goes through. Because the square of this is indeed that, once you make these corrections. And then you can, equally well, you can push everything over to the other side, and so you get the same expression occurring as before, the b squared minus 4ac. And now surely we can go ahead and say, well, if this squared is equal to this, then this thing 2ax plus b must be the square root of that. Now I'll avoid using the square root symbol because we don't really use it in modular arithmetic. That's the convention. So say that this is congruent to u modulo p, where u squared is congruent to b squared minus 4ac. Once you have your u, you can say this is equivalent to x being congruent to minus b plus u. I won't say divided by 2a, I'll say multiplied by 2a inverse. So yeah, we get an equation out for the solutions of the, or get a congruence out for the solutions of the original congruence. But again, you have to be a little bit careful. And I ran it by you fairly quickly, said, yeah, okay, here's the u, such that u squared equals this. But is there such a u? Does such a U exist? Well, the answer, as always, to any kind of question is it depends. Really? You know, it probably depends on the b squared and probably depends on what the value of that is. Maybe. Or maybe every number has a square root of modular p. Okay. So this will all be fine and make sense if, as long as we understand if these square roots exist, if they always exist, or maybe sometimes they exist and sometimes they don't. That raises that question. Okay? So maybe these equivalences are a little bit doubtful now. We need to understand, and I'll put it in quotes, square roots modular p. The reason I put it in quotes is it's not the terminology that is used. Okay, we tend, if you hear someone talking about square roots, that tends to be thinking of normal arithmetic, normal real number arithmetic. The terminology we use in modular arithmetic is quadratic residues. It sounds more fancy, but it's essentially the same thing. Okay, so we can at least begin with a definition, define exactly what it is we're talking about, and then we can maybe start to explore it. Okay, we need to know what kind of an animal we're trying to think about or investigate. So we say that a number or a congruence class V is a quadratic residue modulo P. So this is definition more or less definition 8.1. Talk about 57, although I'm writing it out slightly differently. P is a quadratic residue modulo P, means there exists in U such that is congruent to V. Well, everything is integers, of course. We're talking about modular arithmetic, so we're talking about integer congruence classes of integers, modulo P, that should be understood. So that's what we mean. So V here, if there is a U such that when you square it you get V, then we say V is a quadratic residue. It means V, in the earlier terminology, V has a square root. And we say W is a quadratic non-residue if there is no U with U squared congruent to W modulo. W is a quadratic non-residue if there does not exist such a U. Or another, to relate it to your earlier terminology, if W does not have a square root. So at least we know precisely what we're talking about. We want to understand when a given congruence class is a quadratic residue and when it isn't. So, okay, any questions about the definition? And what we shouldn't do is suddenly start proving a load of theorems about it, because it's a new concept. So we should start to look at some examples and just see what happens in some familiar cases. By familiar cases, I mean, let's take some easy to deal with primes. So let's take some low primes and be able to deal with those. But first of all, a remark. It's not as easy as, you see, when When does a real number have a square root in the normal sense of the word? When it's non-negative. And the negative ones do not have square root. But it's not as easy as positive negative. It's not as easy as positive integers do. And negative ones don't. As every congruence class, mod P. Remember, every congruence class has an infinite number of integers in it. And there's loads of positive integers and there's loads of negative integers in any particular congruence class. So it's not as, the answer isn't going to be as simple as well, the positive integers have square roots and the negative ones don't, because there isn't really, we don't really have a notion of positive and negative in modular arithmetic, at least yet. We might have one when we fully understand the existence of square roots, but it's not, it isn't just, the answer to the question isn't just as easy as the positive ones don't, and the positive ones do and the negative ones don't. As all congruence classes, 1P, contain positive and negative integers. So this is the state we're at the moment, what's going on. We have this idea of sometimes things will have square roots, sometimes they won't. So we're a bit in the dark, so maybe a first sensible thing is to start looking at examples. So first example, okay, I could choose 2 or 3, but maybe they're a little bit too small. There's not much stuff there to see what's going on. Let's choose maybe a little bit more of a richer example is p equals 5. So for p equals 5, I won't bother with 0. 0 is not that interesting multiplicatively. 0 squared is always 0. We don't normally admit 0 into the discussion of multiplication. So when we're talking modulo 5, really we've got four elements around. So which of these have square roots and which of them don't? Any answers?
Well, normally it would be 1 and 4.
Normally it would be 1 and 4. Okay, is it normal situation we're in?
No.
No, it's slightly different because we're talking about multiplication modulo 5, remember? But does that modify your answer? It's a perfectly sensible thing to say straight off. See, now you're being doubtful just because I'm asking the question. No, but it is still the perfectly sensible thing. You know, one way in which we can easily study is let's square stuff. Let's start, you know, 1, 2, 3, and 4 is all there is modulo 5, multiplicatively. So let's just square them all. 1 squared is 1. 2 squared is 4. 3 squared is 9, but that's 4 modulo 5. And 4 squared is 16, but that's 1. So the things you see down here, the things that are squares, is only 1 and 4. 2 and 3 never occur down here. You've got 2 squared, 3 squared, all right, but you never get 2 or 3 out as the answer to square. Okay. So 1 and 4 are quadratic residues. Mod 5. But 2 and 3 are quadratic non-residues. You know, the idea of residue is something that's left after you've done something. So if something is left after you've squared, it's left behind after you've squared, it means it's a quadratic residue. It has a square root. What is kind of pleasing there is half and half. There's 4 things. 2 of them are residues, 2 of them are not. That's kind of pleasing. Also, it tallies with, it at least in this instance, agrees with the notion of square root we already have. 1 is equal to 1 squared in just the normal arithmetic sense. 4 is equal to 2 squared in the normal arithmetic sense. So at least there's some matching going on there. Okay, but let's bump it up a bit. Let's think about p equals 11. So p equals 11, you've got 10 things, don't you? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We're leaving out 0. But everything, every integer is congruent to either 0 or one of these things. Now, which of these are quadratic residues and which of them aren't? Okay. It's not immediately obvious. But we can use the same technique. Rather than trying to stare at them and try and somehow square root them, we go the other way. We just square everything and see what residues are left after you square stuff. So let's square things. 1 squared, that's easy, is 1. 2 squared is 4, it's easy. 3 squared is 9. 4 squared is 16, which is 5. Yeah. 5 squared is 25, which is 3. So speaking modulo 11, remember? 6 squared is 36, which is 3. Can anybody stop me now and just know immediately what all the other answers are?
Yeah, 5, 9.
Okay, how did you know that?
I guess.
That's the worst answer.
And you've got a line of symmetry when you get halfway through.
Exactly. You got a line of symmetry. So where's half?
Between 5 and 6.
So between 5 and 6. See these numbers here, these, and x over here, x equals 3 over here, but when you're speaking modulo 11, 8 is congruent to minus 3. 6 is congruent to minus 5, 7 is congruent to minus 4, 8 is congruent to minus 3, 9 is congruent to minus 2, 10 is congruent to minus 1. And when you're squaring, when you square a minus thing, your part of that is squaring minus 1, you just get plus 1. So that still works the same. So yeah, so that central line is a line of symmetry. So we're just seeing the answer here. These are the residues. So 1, 3, 4, 5, and 9 are quadratic residues. Modulo 11, and the other remaining ones, which are 2, 3, 4, 5, 6, 7, 8, 10, are not. They're quadratic non-residues. Again, we notice this half and half stuff. Half of them are quadratic residues, half of them aren't. That's nice to see. Also, it's nice to see the things that are obviously square integers, of course, 1, 4, and 9. So 1 is 1 squared, 4 is 2 squared, 9 is 3 squared. They, of course, they are quadratic residues because they're square integers anyway. But the 3 and 5 are interesting to see crop up. They're not obviously squares of anything, but modulo 11, they are. Also notice that whereas previously when we talked about p equals 5, 3 was not a quadratic residue, but now when you talk modulo 11, 3 is. Maybe that's not right. You know, why should there be anything special about 3? Because when you change the prime, you're completely changing the context and the rules of the arithmetic. So there's no reason why numbers should behave the same. Modulo one thing as opposed to modulo another one. I mean, we can keep going all night. Let's look at the last example just to see. What do I think? Yeah, if you look at p equals 17, so we want to start doing all this in our head. If you just do all the multiplications, you talk about p equals 17, the residues are 1, 2, 4, 8, 9, 13, 15, 16, and the non-residues are all the remaining ones, 3, 5, 6, 7, 10, 11, 12, 14. It's a pre-prepared example. But we'll just look at the results. I mean, it's not difficult. You just square everything and note down its congruence class, modulo 17. Again, you're getting half and half. 16 things, 16 non-zero things, modulo 17. 8 of them are residues, 8 of them are not. Again, obviously the square integers, 1, 4, 9, and 16 are obviously there as residues because they have, we know what their square roots are immediately because they've got integer square roots. We've also got 4, 8, 13, and 15, which are not square integers, but they are quadratic residues modulo 17. Also notice the 2 and the 8, which were non-residues modulo 11. Now the 2 and 8 are residues modulo 17. So the ones that aren't, of course, the 1, 4, and 9, which were residues modulo 11, they still have to be residues modulo anything else because 1, 4, and 9 are inherently the square of something because they're a square of something in regular arithmetic. But the other ones, the other ones which are not obviously squares, sometimes they're non-residues, 2 and 8 here, modulo 11. Sometimes they're residues, 2 and 8 here, modulo 17. So we haven't discerned any pattern there. Okay. So some observations that might inform what might be the first theoretical results we can establish is that there seems to be, so p minus 1 over 2 residues each time. We've only looked at 3 examples, but it's suggestive. So there's p minus 1 things in total. There seems to be half of them seems to be residues. And of course, by definition, p minus 1 over 2 non-residues. Square integers, such as 1, 4, 9, etc., seem to be always residues. I mean, I think we can be pretty confident that that's a fact. 4 will always be the square root of 2, no matter what the modulus is. 9 will always be the square root of 3, no matter what the modulus is. Just the way multiplication modulo something works. So at least we've got 2 observations. I mean, we shouldn't be that confident that it's always half and half, maybe just from 3 examples. But at least it's suggestive. One other thing maybe to experiment with is, because when we talked about square roots in normal arithmetic, the criteria for having a square root was that you are positive. And if you're negative, you don't have a square root. And in some sense, the positive and negative is a kind of half and half, a 50-50 splitting of all the real numbers, to talk loosely. What we're seeing here seems to be a 50-50 splitting of all the congruence classes modulo prime into things that have square roots and things that don't. So we might ask a question, are we seeing any connection with positive and negative? With the idea of positive and negative? That's a rather vague question, it's not very precise. One way in which you might answer yes to that question, in that we might be seeing some kind of connection, is, you see, we know very well how positive and negative numbers multiply. If you multiply two positives, you get positive. If you multiply two negatives, you get positive. If you multiply a positive and a negative, you get a negative. Those are structural rules about being positive and being negative. Product of positives is positives, product of negatives is negative, is positive. But if you multiply one of each, you get a negative. When you test that out here, if you multiply two residues, so 8 by 9. Okay, 8 by 9 is 72, but what is it congruent to? What's this? This is modulo 17. 8 by 9 is 72. What's that modulo 17? 4 times 17 is 68. So 4. And yeah, 4 is a quadratic residue. So you multiply 8 and a 9, you get a 4. If you try something else, multiply 2 by 13 is 26. Modulo 17, that's 8. 2 by 13 is 26. It's 8. Modulo 17, and 8 is up there as well. So, yeah. You pick a pair of residues, multiply them, you seem to, well, I've only done 2 examples, but it seems to be working out that you get a residue. If you multiply one of each, like a 4 by 10, which is 40, modulo 17, 40 is 2 times 17 is 34, so 46. And yeah, 6 is down here, a non-residue. So multiplying a residue by a non-residue, you get another non-residue. If you multiply together 2 non-residues, which should be like multiplying together 2 negatives, so 3 times 7, 21. 21 modulo 17 is congruent to 4. 3 times 7, yeah, their product is up here. So it's a little bit of a jump. Okay, maybe we wouldn't have naturally seen that already, but with a bit of prodding and knowing that already there might be some connection to positive and negative, you can see that here. They seem to follow, okay, just from looking at one example and a few products, but they seem to follow the rules residue times residue is a residue, non-residue times a non-residue is a residue. And when you do one of each, a residue times a non-residue, you seem to get a non-residue. So you start to see some of the properties that we might be able to prove. And also, there's something we haven't seen so far. Something we haven't seen so far really is any kind of pattern with regard to when a number is and is not a residue, apart from the ones that are square integers already. So like 2 is a residue modulo 17, but it's not modulo 11. And it wasn't modulo 5. So another observation is kind of still a stark question for a non-square integer. So something that isn't obviously a square. how can we tell if n is a residue on P? That's a general question. Is there any, okay, we can always figure it out just by squaring everything, and just seeing what there is. But is there any sensible way in which we can answer that question?
Yeah, you could take the squares, so for example, 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, and then you mod it all by P.
Yeah.
It would get you on.
Yeah, so you can just work it out by brute force. You can certainly like list all the 18 numbers 1 to 16, square them all, and you'll see these ones occur as the squares and those ones as not. So that's always a way we can approach it. But I mean, how can we tell if or understand when? Is there anything better we can do apart from that? Just kind of square everything and see how the cookie crumbles, so to speak. Is there any way to know in advance? Is there something about 17 that means 2 is a residue, but there's something about 11 that means 2 is not a residue? Is there something to discover there? Is there some pattern there? Okay. Well, there might be, there might not. But this being mathematics, we hope there to be a pattern. And hopefully we can discover that and prove it, establish it. So any questions just at the moment, or any clarification? So hopefully I've persuaded you that it's a kind of an interesting problem, that by looking at some examples, you can start to see some of the things that might be true. This half and half looks quite strong. This property of multiplying them by each other seems, well, we've only looked at minimal examples, but we would hope for that to be strong, especially since it's to do with square roots, and that is the way that positive and negative numbers work with square roots, with a multiplication. Then we're still faced with this question here, which we don't really see any clear way through at the moment. Okay? So I'll be seeing you again for the lecture tomorrow afternoon. We'll start to make some headway with some of these things. Then. So in the meantime, if you're reminded to do some work on this evening in advance of that, you could have a go at these questions here. These are just questions that are just leading you through some more exploration of some examples in advance of starting to work through the theory on that.